geographic data. And this is one of my favorite topics because it's really fun, but it's also always a difficult topic because this is not an area that I'm like a super expert in. I've created tons of maps at this point, but I'm not like you know, I'm not in the geographic department, um, geography department. So like it's a little bit outside of my comfort zone. Um, but there's so much about this topic, right? It's a huge, huge topic. So today we're only going to have a little bit of a taste of it, okay? So we're only going to be talking about visualizing geographic data. Obviously, there's all sorts of geographic analysis stuff that you can do too. We won't be talking about any of that. The basic learning objectives today are I want you to be clear by the end on the difference between vector and raster data, and we'll get to that pretty much right away. We will mostly work with vector data. And I would ideally like you to be able to produce basic maps and be able to do that by obtaining geographic data from a few different places, okay? So there's lots of different places you can get geographic data, and at least one or two of these should be available to you. By the end, you probably won't actually be able to do it with me today, but maybe you could be able to produce basic interactive maps. Okay, there's a couple of different packages that make it astoundingly easy to create a basic interactive map where you can pan around and click on things and zoom in and zoom out and all of that stuff. And finally, just to understand the basics of the R geospatial ecosystem. Just about, say, like 4 or 5 years ago, the geographic ecosystem in R was nascent, right? There were packages out there that would do things. ggplot has been quite powerful in this regard for a long time, but the whole ecosystem has really expanded in the last couple of years to the point where many geospatial professionals work in R entirely, which was not the case not very long ago, okay? And that's mostly because of the work of a few really dedicated people. So today, I just want to be clear, today is partially about the content and hopefully that you'll be able to do some of this stuff. It's also partially about exposure, okay? So I want to sort of just expose you to some of these ideas, and then if you want, later you can come back and really study the slides and be able to produce some of this stuff. But a lot of this is actually quite straightforward to produce, and so you may be able to follow along and do some of it. The only problem is with maps generally is that when you create maps, there's so many lines and so many things that they can be quite heavy, right? And what I mean by that is like they can take a while to render, and after they're rendered, they're such like dense objects on your computer that it can just take like quite a long time. So following along might be a little bit difficult, but you can try if you want. I also want to give you resources to learn more. This is probably my favorite place. These 3 authors are all 3 of the main people that have really done a lot in terms of pushing R forward in the geospatial world. And this book has pretty much everything that you would want to know to have a really good foundation in geospatial analysis. For some reason, my HTML thing isn't coming up here, but there's also a 2-day course from a guy named Zev Ross that he gave at RStudio Conf in 2020. And some of the materials in this are actually from him, from that presentation. You can go to his link. I don't know why this isn't working, but if you look at it on a different browser, it might. This is sort of like what I was referring to, though, about maps being rather heavy. These slides take the longest to load of any slides that I have up there, too, because there's so many maps in them, okay? But anyway, that's another good place to start, okay? So the first topic I want to talk about is vector versus raster data, okay? Most of what I do, anyway, is vector data, okay? Vector data it means you have lines and you have points and you have basically geometry, right? You have longitude and latitude and associated lines or points or polygons, right? So it's essentially like, you can think of it in terms of a map. You have like data that instructs R, whatever tool you're using in R, how to draw the map, how to draw the road or the river or the polygon for the county or the state or whatever, right? Raster data is different in that often raster data is literally just a picture, okay? And then what happens is you split that picture up into a bunch of different cells, and then those cells get assigned values depending on what's in the cell. So if you think about like a typical black and white picture, the value in the cell might just be saturation, right? How much ink is in that cell. And then you can use that to plot the data, right? So as I sort of already mentioned, vector data is points, lines, and polygons. And so very often this is used in social science sort of worlds, because we're using sort of made up boundaries a lot of the time, like human made boundaries, right, to explore things like counties, right, or states even. And so we have these polygons that we're drawing on the map, and then we can fill them based on the number of people that are there or whatever, right? Generally, these come in shape files, .shp, but there's also other formats like GeoJSON. And also there's quite a few R packages that these data are released with. So you just load the R package and you all of a sudden have the data available to you. For a lot of stuff, that's going to get you a little ways, but it's not going to get you all the way there. And part of the reason is because, again, like many of these files are themselves rather heavy because it's a lot of data associated with the thing, okay? So this is what we'll talk about most of today. Raster data, you just divide the area into a grid and then assign each square a value. This is common from satellite images and remote sensing data sort of stuff, okay? So this can occasionally be helpful in social science too, though, because there might be things like weather that we're interested in showing that are related to social science phenomena, but also we can use it to show things like population density in a slightly different way. This is a graphic that came out from the New York Times just a little while ago, just maybe a week or two ago. This is a great example of mixing vector data and raster data. Okay, so the vector data is obviously like the country and all of the states, but then the raster data is the actual temperature. Okay, so you can see if you look close, those are all just a bunch of little teeny squares, right? And then those get shaded according to this temperature. This is also, I think, just an excellent map generally. You have this like annotation here that shows these like regions of temperature, which is really nice. You have the direct labeling there, which is really nice. And then all of the states are labeled too. So I think this is an incredibly clear and really nice plot. If we click here, this is the source for it, and you can see, so this is entirely vector data, right? Even the fill down here, right? Those polygons are filled by percentage of customers without power. So this is entirely vector data, more vector data. Now we've got raster data on there, okay? All right, these are some of the packages that are in the R spatial ecosystem. SF stands for simple features. That's it's probably, to me, it's been like the biggest game changer in terms of working with spatial data in R. It's really nice because you end up having a data frame that looks and feels and works much like a regular R data frame. The difference is you just have this column at the end, which is usually called geometry, but it could be called points or line string or whatever, but it's a list column, okay? And as long as you don't go into that list column, then all is good. And you're just basically working with like a normal data frame. You can join with other data frames very easily. and all of that sort of stuff, okay? So that's a really nice package. Raster, we're not really going to talk about much. ggplot, of course, can be used to create the plots. tmap is an alternative to ggplot that is also super powerful. It's called tmap, meaning thematic mapping, okay? So I'm going to show some examples near the end of using tmap because it's, especially if you're doing a lot of plotting, it's really worth investigating, okay? I tend to always work in ggplot just because that's where I'm comfortable, but tmap is really nice and has a very sort of similar feel to it, to ggplot, okay? And then we'll talk about map view just a little bit at the end. That's a really nice package for just taking a basic plot and turning it into an interactive plot. So my goal for this lecture is to take you through at least a basic tour of each of these, and except for raster, okay? But we will discuss raster data a little bit. And please stop me anytime if I'm going too fast or if you have questions on any of this, okay? Geospatial data generally has quite a few challenges that are not there with typical data analysis stuff, or rather other data analysis stuff that we're doing. One of the first is coordinate reference systems and projections, okay? We won't talk about this too much today, but I want you to be aware that that is absolutely a challenge. If you are plotting some data and you have the wrong coordinate reference system, or you're using the wrong projection, then your polygons, showing your thing, whatever it is, are going to be skewed. And there's a whole bunch of research on this for different areas of the globe and what coordinate reference systems work well. And then projections are like their own thing altogether. But if you just do a little bit of research on the area that you're working with, you will find probably references to the coordinate reference system and projection that have the lowest error. So how far off they actually are from reality. And part of the challenge with this always, right, is that the Earth is a circle, like a sphere, basically, right? And so it's got this curvature to it, and we're always trying to plot it on a flat thing. And so you end up with some error there. The nice thing about the SF package, though, is that unless you're building your data sort of on your own, the vast majority of the time, that coordinate reference system for whatever you're plotting is just going to be embedded with it. So you're not even going to have to worry about it most of the time. Not always, but most of the time, okay? And similarly, it'll just use the projection that works the best. This gets particularly challenging, though, when you move to the poles. So if you're doing something, say, in Antarctica, and you want to plot, whatever, ice, polar ice or something, then this is absolutely going to be something you're going to want to pay attention to, okay? There's also list columns with SF in particular, which I mentioned already. We're going to talk about list columns a lot in the next course. They're super powerful, really, really nice. But if you're unfamiliar with them, then it might be like, feel strange and foreign, right? My recommendation is to just not worry about it. Just let that column be there and just don't ever touch it and just go on, all right? You also do have different, with vector data, you have different geometry types. So lines versus points versus polygons, etc. Vector versus raster data. And then data import, most of the time, is not that big of a deal, but sometimes it is. And sometimes, especially with raster data, right? Because you might have, let's say, remote sensing data for a specific area, and then you have that over time, right? So you have it for one day, then the next day, then the next day, then the next day. And that's great data, but the way that data is typically stored then is in a data cube or data brick. So like you'd have that 2D landscape stacked on top of each other where each layer is a new day, right? And so that can be a little bit difficult to conceptualize and work with and things like that too. Okay, we're only going to talk about a couple ways of getting spatial data, and it's pretty purposefully United States centric. There are lots of places where you can get other data, but I wanted to focus specifically on getting census data, okay? And unfortunately, getting census data requires that you have an API key. It makes a lot of sense that that is the case, but I say it's unfortunate because unless you already have a census API key, you probably won't be able to follow along with that section, but you'll be able to come back and visit the slides, okay? Generally, if you have .shp shape files, it's not super difficult to get data in or out, but raster data tends to be a little bit more tricky. And like I said, there's lots of different organizations and things that are publishing our packages. Okay, so working with spatial data, there's basically two options. I've mentioned SF already, simple features. There's also this SP package, okay? SP used to be the standard for working with spatial data in R. There's these spatial whatever data frames. So spatial points data frames, spatial lines data frames, spatial polygons data frame. They don't look like normal data frames at all, right? They look like basically giant lists with all sorts of other things in them. They do have some operations that work like a normal data frame. But what I do is if I end up with an SP object, I just immediately convert it to an SF object, okay? So that's what we're going to mostly focus on today. I don't really feel comfortable with SP objects at all. I think SF is, there's nothing you can't do generally with SF objects that you can do with SP objects, at least that I've found. So I just immediately convert it to an SF object because then it's much more familiar and easy to work with. So this is how you do that. SF being the package, obviously, you just do st as SF, and it'll convert the SP object to an SF object, okay? If you want to know what an SP data frame looks like, once we get to the point where we're actually getting some data, you can do that and just print the data frame. I'm not going to do it because it takes time and it's a big, long thing that's hard to look at. But if you want to look at that, feel free. Okay. All right. So the first package I wanted to mention in terms of getting spatial data is called Tigris. Okay. And you should not need a census key to get this. So if you want to follow along here, I'll give you a minute. Go ahead and install, if you haven't already, the Tigris package as well as SF, okay? And then load both of those packages, and then we'll do this, okay? This is probably going to take a while in terms of rendering time. So I'll give you a minute to do this, and then go ahead and try running this line of code. This options part is if you want it to be an SF object or not. Okay, so if you say options Tigris class equals SF, then as it goes and gets the data, it will just automatically convert it to an SF object. If you don't want to do that, then you can print it out as SP object to see what that looks like, just so you have some sort of awareness about it. But then I would recommend going ahead and doing ST as SF on your thing, whatever it is, okay? So I'll give you a minute to go ahead and do that if you want to follow along. And if you have gotten that done, please give me a thumbs up so I know where we're at time-wise. And if you're having issues, go ahead and just unmute and let me know what's happening. Give you about one more minute if you're not there yet. All right, looks like we're mostly there now. Okay, so I'll just talk about this a little bit more while the last few people are finishing up. So basically, you're just going to load the packages, obviously. I mentioned what this options Tigris class is doing, right? Making it so when you download it, it's as an SF library or SF object rather than an SP object. And then Tigris just has all of these different functions that allow you to download spatial data, right? So this one is from Tigris. It's just called roads. And so you say roads, you say the state you want, and then the county you want, and it'll get you all of the roads for that county, okay? You can also do, I think, towns, but I'm not 100% sure on that. Maybe not every town, but you can do states. So you could get all the roads for an entire state. You can do whatever, right? So when you do that, then I can print out roads lane co, and I get some stuff here that tells me some information about the place, right? So this is the name of the road. And then over here, this is that list column, okay? So this is a line string, I think, right? So it's basically just a road that is just this long line, okay? Once I have that, this is an SF object, right? Because I've used that options, or if you haven't done that, I would recommend converting it to an SF object with ST as SF. Okay, let's say now I don't want to continue to download this every single time I run my script, right? Because that would be silly. So instead, I'm going to go ahead and write this file out to my computer, okay? That way, when I want to access it, I can just read it in, and I don't have to worry about downloading it every single time I render my script, right? Then I would just use write SF, take my object, and then say where I want to write it to. The only thing that's a little bit different here is that I have .shp as the file extension, okay? And that'll write a shape file to your local hard drive, all right? Then when I'm ready to read it in later, I just say read SF and then put the path to the file, and there it is, okay? And now it's exactly the same as when we just downloaded it. So if we're right, and the reason I'm illustrating this obviously is not just for this example, but if you come across shape files you want to read in, this is how you would do it, right? And then writing shape files is fairly common too if you're working with the same file over and over again. Okay, so that's pretty straightforward. Now let's say we want to plot it, okay? All we do is use geom_sf, okay? So you can take your ggplot object, say roads lane co is what you want to plot, and then plus geom_sf and put a color, okay? This depending on your computer and everything, may take actually a decent amount of time to create, but you can go ahead and try that if you want. And while you're doing that, I'm going to move on and show you additional things that you can do. Okay, so this is still with the Tigris package, but what I'm doing here now is I'm saying, okay, add the lakes for the county. Okay, so there's this function area water. Okay, and I'm going to say for Oregon Lane, again, that's going to find the bodies of water in Lane County. Okay, and then linear water is going to find streams and drainages and all sorts of things like that. Okay, so this is now I'm adding all of the water to Lane County, the lakes and the streams and rivers and drainages. Okay, when I produce this now, notice I'm not putting any data set in this top layer. The reason is because my data set is actually changing for every single layer. And this is a fairly common thing when you're producing maps with ggplot. The data source changes with each layer. And so I don't want to put a data source at the top layer because anything I put here is by default going to sort of bleed through to the next layers. If I put the data source on the individual layer, then it's only going to affect that layer. And that's true with all of ggplot, right? But so what I'm doing here is I'm saying, okay, here's ggplot. My first geom_sf layer, I'm going to add lakes. My second geom_sf layer, I'm going to add streams. which are just these two objects up here, right? Both SF objects because I had set my options to be that. And then my final geom SF layer, I'm going to add my roads. Okay, so this is like a blue color here, and then that gray 60 for the roads. When I do that, I get a plot that looks like this. Okay. And so I'm not advocating that this is like the greatest plot in the world, but you can understand fairly quickly how this would grow, right? How you would build a plot like this. The other thing we can do is we might want to limit the boundaries of this because I guess it, Eugene, at least, is not available through the Tigris package. So we had to get all of the data for Lane County, but maybe what we're really interested in is just Eugene. Okay, there's another package called OSM data, which stands for OpenStreetMap data. And it's another really nice one for getting all sorts of data from OpenStreetMaps. Okay, so we'll get street level data. And what we're going to do is we're going to use this function getBB, which stands for get boundary box. Okay, and I'm going to say get the boundary box for Eugene. And that's all I have to do is just say Eugene, and I get this boundary box. So this is now the coordinates for a box around Eugene, okay, that we could limit our data to. Okay, so now I'm taking my same exact plot I had before, but I'm just using this chord SF, and I'm saying limit the x-axis to the first row, right there, and limit the y-axis to the second row, okay, here. So it's just giving me the boundaries of Eugene, basically. Okay, when I do that, now this is what I end up with. Okay, so this is fairly neat, I think. But we can also do the same thing fully through OSM data. And OSM data, the OpenStreetMap data, is a little more detailed. So what I'm doing here is, so this is like sort of an aside thing. This is not super important, but something I want you to be aware of. Okay, I'm doing this fully through OSM data. So I get my boundary box. And then for my roads, rather than using Tigris, I'm taking my boundary box and I'm saying, I'm passing that to this function called OPQ, which stands for overpass query. All right, and that's doing a query to the OpenStreetMaps API. Then I'm saying add OSM feature highway. So add highway features to this map, and then switch it to an SF object because by default it's SP. Okay. Then I do the same thing, but I say add OSM feature water. Okay, now I have a roads and a water. And now when I plot these, I'm going to do it like this. Data is equal to water polygons. And then I'm going to fill it with this color. And then the outline is just going to be a darkened version of that color. And then water polygons again. Oh, this is the multi-polygons. So this is like lakes, I believe, and this is streams or something. I don't know. I can't remember anymore. And then here we're adding the roads. So this is roads OSM lines. So basically each of these objects has multiple things that I can pull from it, right? Multi-polygons, polygons, and lines from the water one, and then just lines from the roads. Limit the boundary box again, and then just add a caption that says Eugene, Oregon, and we end up with something that looks like this. Okay, this is actually, you could sell that on Etsy probably, right? Like, it's kind of amazing how detailed that map is, and it's not terrifically difficult to do, and you could do it for any city in the country, right? So again, that's just sort of a side thing. But were people able to get like this basic map to render? Did it take a long time? Yeah, all right. It's going to probably vary by computer too. Okay. All right. Now I'm going to move on to getting census data. And so this is where you probably just have to watch for a little bit because you probably don't have an API key. And if you do, then great, but you'll have to get set up with using it through R quickly. So this is like sort of real basic instructions on how to do that part, right? So here is a link to request an API key for the US Census, right? Super easy, and they'll just email you later and give you one. And then once you have your Census API key, you can use it in one of two ways, all right? One is so we're going to use this package called tidy census, okay? So this is a function from that package, tidy census, called census API key. And you could just put this at the top of your script, right? Census API key, and then you would put in a string whatever your key is. This is probably not the best way to do it though, because your API key is for you, right? It's only meant for your use. And the reason is it's like sort of like a fingerprint, right? So the US Census can essentially track who's accessing their data, right? And this is in part because if you're making like 1 million requests, then they might contact you and be like, hey, calm down, like, what are you doing? Right? So so that's probably not the best way to do it. Better is to edit your R environment, your .r environ file. And you can do this by using this function from the use this package. Use this, I think I've mentioned this before, but there's a package called use this. It just automates a bunch of routine tasks. It's one of the most underrated packages that exists, I think. It's an amazing package. I love it. Okay, one of the things that it has though is this edit R environ function. Okay, and all you have to do is run that code and it will bring up your .r environ file. Okay, then you're just going to add this census API key equals, and then in your string your API key. Okay, and then that file never gets committed anywhere. It actually lives in a different location outside of your project, so you never have to worry about committing your API key to a GitHub repo, so now it's publicly available and anybody can grab it. All right, so that's the way I would recommend doing it. Once you have that, then it's actually crazy how well this works and how much data you have access to like right away. Okay, so we go library tidy census, and then I have a little bit of code here to show you how to search variables. Okay, you can search variables directly through the Census API, but this is a pretty nice way of doing this, right? So I'm creating a variable here called v, and then I just use from tidy census load variables, right? I give it the year and the survey I want the data from. And let's just go to tidy census real quick. So it's by this guy, Kyle Walker. He's super good, super nice guy. But if we go here, all right, this has a lot of that same sort of information that I was referencing. But the main, let's see. Yeah, so the main data sets that it uses, I think, are the ACS, or surveys rather, the ACS and the decennial survey data. Okay, but the ACS is typically what I use. So this is me getting data from 2018 from the ACS5 survey. Okay, so this is loading all of those variables. And then if you just use view on V, then you can just sort through it as like a data frame, and you can search and all of that stuff to find variables you're interested in. Okay, now I'm going to get some census values. I'm saying my geography is going to be a tract. Okay, and if you're not familiar with census tracts, they're another sort of made up thing, but they're nice because they are they change over time a little bit, but they're geographic boundaries that are created based on population density. Okay, so they're supposed to center on about 2,000 people in the boundary, and but it can range anywhere from like basically 0 to not 0, but you know, like a small amount to like 8,000 or something like that. But just by plotting these tracks, you can get a basic idea of the population density of an area. Okay, so I'm going to get tract data for all of Oregon on the median income and the educational attainment of Oregon, okay? And these values here are just what I found through this load variables thing, right? So every variable has an associated code. This is an example of how I would get those, okay? From the year 2018, and then I also have this geometry equals true, okay? And the reason I want that is because by default, it's not actually going to grab the geometry. It's just going to get the track number and then this information that you asked for. But you can just say geometry equals true, and it'll grab the actual geometry for those as well, okay? Then it's loading it. That's what all of this is right here. And then we can look at the data, and it looks pretty much like a normal data frame, right? We get this geographic ID, the name, and then we have this variable column. So you can see by default, it's in a long format. You can also request it to be in a wide format. But we have the median income and the educational attainment for census tract 9706, okay? And then same thing again for census tract 12, etc. Okay? Over here, we also have, so this is the estimate. You can barely see it. Right here is the MOE, margin of error. And then we have the geometry right here. Okay, so that's that column that we're probably not really ever going to pay attention to, but that's what has all the polygon information that we need. Okay, so now we're going to plot it. So I'm going to use color space just to get a different color palette. And then I say geomsf, so census vals, geomsf fill equals estimate. And I'm going to go ahead and have the color be the estimate too. So the outline of the tract is going to be the same color as the fill of the tract. Okay, and then I'm going to facet wrap by a variable. So I'll have two maps of Oregon, one for educational attainment and one for median income, okay? Guides color equals none. That's just going to omit the color scale, and then scale fill continuous and scale color continuous. I'm going to use this blue, red, 3 palette, and reverse equals true. So I'm flipping the scale. And I get something that looks like this. Not quite what I was looking for, right? It's okay in terms of the tracks and things are filled appropriately, but the problem is I'm using a diverging color palette that by default is going to center on 0. And I don't actually want it to center on 0 because 0 means none, right? So what I probably want it to center on, if I'm using a diverging color palette, and you could argue the merits of that, but I'd probably want it to center on like the mean of these variables, right? And so that would allow you to very quickly say, okay, if white is the mean and red, then red is going to be less than the mean and blue is going to be more than the mean, right? So you can very quickly scan the map and see which areas are around the mean and which areas are below and above the mean. So let's do this again, but we're going to do it just for each map separately because these are on really different scales. And so we could scale them too. That's another way we could do this. But you can see, right, educational attainment is essentially all white relative to median income, which is going to be all blue. So let's try one at a time. All right. So here I'm creating a variable called, or an object called income. I'm taking census vals and I'm saying, okay, just give me the rows where variable is income. Okay. And then I'm doing the same thing, but notice right here on this scale fill continuous, I'm saying the midpoint of this scale is the mean of estimate. Okay. And I do that for both the fill and the color. Okay. At the bottom, I'm just switching the legend position so it's at the bottom instead of on the side. And now I get something that looks like this. So this is quite a bit better, I would argue. And in part, you see rather quickly that in terms of income, the Portland area is a lot higher income than the rest of the state, right? In fact, outside of this county, or tract rather, the state is mostly below the average because the Portland area is so much higher. Okay, so that's interesting. We can do the same exact thing for educational attainment, and we see a sort of similar pattern, but a little bit different, right? And then we can put them together. We could probably use patchwork. I don't know why I didn't use patchwork here, but now you can get a sort of basic idea of how these variables go together. Okay, grid dot arrange, just put the two plots and then say number of columns equals 2. Patchwork would have been just P plus P2. So I don't know why I didn't do that, but regardless. Okay, does that make sense for the most part? Even if you weren't able to follow along. Any questions on that sort of thing?
Mine got a little wonky at that last chunk. It didn't see income variable. I was just trying to go as fast as I could, but when I got to the last bit, it just said object income not found.
Okay, so did you create the income object
I thought
right
I had that whole thing. Did I need to run that as a separate? It was part of that code chunk that I had.
Yeah.
It just didn't see.
If it's saying object income isn't found, you probably didn't get this line run somehow.
I mean, like when I look at the data, the census data that came down, I don't see. Oh, I see a median income variable.
Yeah, so the variable should look like this, and then it should have rows for.
So I'll try and just run that particular line.
Yeah.
By itself and see if that lets me do it.
Yeah.
Error in data matrix. Object cannot be coerced to type double.
Okay. Well, we'll
no
look
biggie.
at it together. Yeah. It works for me because my slide's rendered. So.
Yeah.
All right. Okay. So the next thing I want to talk about is definitely a. You'll have to come back and study the slides if you want to do this, most likely thing, right? This is kind of an out there thing. It's sort of a newer experimental thing, but I think it's really neat. And it's something I played around with a lot because I got interested in it. So I just wanted to share quickly here the idea of bivariate color scales. Because in situations like this, we can put two maps together like that. But what we're really interested in often when we have this sort of thing is essentially like the correlation between educational attainment and median income for an area, right? And so what we can do is create these bivariate color scales that have like a matrix of color values, and then we can fill the area based on where it fits in there. So here's an example of an amazing map, I think. This is by this guy, Timo Grossenbacher. I may have even showed this before, but this is an example of using a bivariate color scale, right? So he's got this inequality measure and then income. And so you can see this moves to higher inequality and this moves to higher income. So like this dark blue is low inequality and high income, whereas this dark purple is high inequality and high income. So you can kind of look through the map, and as long as you're kind of referencing the legend, you get an idea of how these two variables go together. Okay, so I think this is a really neat idea. There's a bunch of different ways to do this. Probably the best way, or the most common way anyway, is to take your two continuous variables that you're interested in and you just break them up into categorical variables. Then for each combination of those categorical variables, you assign a color value. So then you have, rather than having two continuous scales, you have 6 colors or whatever, right? So this is an example of that, where higher inequality and higher, well, so inequality and income are both continuous variables, but they've been split so that they each have 3 bins, right? And then for each bin combination, we assign a color value, all right? The problem is you have to be very careful about the colors that you use. Okay, so this is another example where we're taking 2 color palettes and we're combining them to get a bivariate color map, right? And so I think this is really neat, but I would be very cautious if you're going to do this and only use bivariate color maps that other people have created, basically, unless you're really comfortable with combining and mixing colors and you're confident you're getting the right colors. Okay, so this is 2 sequential scales basically that are being combined to create this bivariate color scale. All right, and again, like the reason this is important is because it has to have this low to high perception this way, low to high perception this way, and sort of on the diagonal as well, right? So it has to, and it has to map for each row and each column, right? Okay, so this is going to be fairly quick. I'm going to move my data to a wider format. I have to use spread here instead of pivot wider because I don't know why. SF has not yet incorporated pivot wider into their workflows. At least it doesn't seem to work for me. Spread is the old version of pivot wider. So basically this is the variable and this is where the names are coming from and this is where the values are going to be filled from, okay? Then I'm just going to drop NAs. All right, so now you can barely see down here, but I have all of my census tracts and now I have a column called ed attain and a column called med income, all right? Now I'm going to find the quartiles of each of those two columns, okay? So I'm saying ed quartiles and income quartiles. So I'm taking this quantile function, feeding it the value, and then saying, give me the probabilities of that from 0 to 1 with a length out of 4. Okay, so if I just look at ed quartiles here, you can see I've got 0, the 0th quartile, 0, 33rd, 66, and 100. So it's basically these 4 areas, right? What these are going to end up being is essentially cut points, where I'm going to say, if it's between here and here, it's in one category, right? If it's between here and here, it's in a second category. And if it's between here and here, it's in a third category, okay? So this is like low, medium, high, basically. Okay, so that's what I'm doing here. I'm taking my wider data frame. I'm creating a new variable called cat ed, categorical education, and categorical income, where I'm going to cut that variable, that ed attain variable, according to these ed quartiles, okay? And I'm going to cut med income according to these income quartiles, all right? Then I'm just going to select those variables so we can just see what it looks like, okay? So this is cat ed. It's between 54 and 2.68 plus 0.3, all right? This one is between this value and this value, okay? So that's how it cuts them, all right? Now we're going to create the palette. And so what I'm doing here is I'm just going ahead and dropping the geometry for a second, and I'm just going to count these two variables, cat ed and cat income. That's going to give me all possible combinations, right? Then I'm going to drop NA, and then I'm going to mutate to create a palette, okay? And these are the values of the palette. I got those by using color slurp on that palette to just grab the 6 values, okay? And so here's the palette. And this is now a data frame called pal, right? That just has the corresponding palette for each combination of cat ed and cat income. Okay, so there are these 9 possible combinations of the 3 possible values for each, right? And I'm assigning a value to each of those. Finally, I'm going to join that data set back with my map data set. And then from there, I can just create the map, okay? So I'm saying ggplot, geomsf, but now I'm going to say fill and color according to pal, okay? Because there's going to be a column called pal, just like this, in my actual data set. I'm going to say fill and color none for the guides, or for the legend, basically. And then I'm using these functions scale fill identity, which means it's going to pull the color from the actual column, scale color identity, and we get a map that looks like this. Okay, so that's cool, but the problem is we don't have a legend here, and it gets really difficult to know what's going on. So we have to create a legend on our own. So this is just I'm creating a plot here that I'm calling leg, right, legend, and it's just basically a heat map sort of thing that has those values, okay? Then what I'm going to do is just add that legend. So I'm going to put the 2 plots together and I get something that looks like this, okay? So I know that's super quick, but basically this part, I'm putting those 2 maps together, and I have to change the coordinates to put this plot where I want it to be on the map. And that's just basically guess and check, okay? But now we can look at this map and you can kind of see higher education versus higher income and how those two things go together. All right. So I know that's super quick, but that's very much just I want you to be aware of it because I think it's really neat and I think it's a cool way to do this sort of thing. Questions on that? Okay.
I actually do have a super basic question. You used cut as a function, and I don't know what that is. And I feel like, is n-tile doing the same thing as the quartiles and the cut put together? Is that what that is?
I'm not familiar with that function, so I don't know. Probably. Cut just takes a continuous variable and then puts it into a categorical variable based on whatever you feed it, like what you feed it.
Okay, awesome. Thank you.
Any other questions? Okay. All right. So now I want to move away from ggplot for a minute and talk about tmap. Okay. So like I said, I mostly use ggplot because that's where I feel most comfortable. And if you don't ever want to go to tmap and you just want to do ggplot, that's totally fine too. But I do want to make you aware of tmap because it is super powerful. It can do all sorts of things, including moving a map from a static map to an interactive map like nothing. You just have to add one line of code, right? So it's really nice. It also, as Chris recently mentioned to me, which I was not aware of this, it can be much faster than ggplot as well. So you can have a plot that's taking a long time to render, and you try to produce the same plot with tmap, and it's like almost instantaneous. Okay, so that's another reason that you might want to look into tmap if your plots are taking too long to render. Okay, so going to the education map again. Okay, we just load tmap, so you'd have to install this first, obviously. But then what we're going to do is we're going to say tm shape. Okay, and for each of these, each time you do tm shape, you're going to have to add another layer onto it. Okay, so tm shape wider, this is the data set I'm using, right? Same SF data set I had before. And then I'm saying plus tm polygons med income. So it's going to add those polygons and it's going to fill them by the median income. And that's it. Create this map. Okay. We can facet as well. So now I'm going back to my census vals one, say tm polygons estimate plus tm facets variable. And there we go. There's also other ways to facet, but for some reason, there's been updates to tmap since I last gave this lecture and I couldn't figure out how to do it. But it used to be you could just on your tm polygons give it 2 variables and it would facet. So I think there is a way still to do that. It's just probably slightly different syntax now than it used to be. You can change the color again, fairly straightforward, right? tm polygons editing, just say palette equals magma or whatever you want to use. You could use a palette from a different package as well. Border color, line width on those borders, whatever, you end up with this, okay? You might want a continuous legend instead of a categorical legend because by default, notice it's categorical. And then I've also put the legend on the outside, legend.outside equals true on tm layout. Okay. And we can also add text. I think this actually didn't. Okay, so what I'm going to do here is because I don't want to add text for every single census tract, right? That's going to be too much. So what I'm doing instead is I'm going to just plot counties for Oregon. Okay, so I'm getting ACS geography is equal to county instead of tract, state Oregon, and I'm only grabbing educational attainment this time, not everything, right? Year 2018 geometry equals true. Okay, so now I have this object called county. Looks like this, and this estimate is just the educational attainment, right? And then the margin of error. What I want to do ultimately is put a label on each county to say the county name. All right, but what I'm doing here is I'm computing the centroid of the polygon. So each county is a weird shape, right? And I want to compute basically the center of that shape. That's what this ST centroid is going to do. Okay, I will probably get a warning about some planar assumption. So it's assuming like a plane rather than like the curvature of the Earth, but whatever, it's going to get me close enough. All right. Then I'm going to get the actual name by say county string replace all name, basically get rid of all of that and replace it with this, with nothing. Okay, and that'll be just the name instead of County Oregon. And then this is the code that actually works. For some reason, it doesn't work on my slides. I don't know why, but it does when I was working with it locally. And I think that's just related to some of the CSS stuff I have, because for a while I couldn't even get the interactive maps to work on my slides either, which was highly annoying. But I found the CSS part that was messing that up. So this should work for you, even though it's not here. All right, and then what we would get is like a little, you know, text of the county name for each of these. All right, real quick, I wanted to also talk about raster data, at least a little bit, okay? Sometimes we might want to do things like get elevation data. I can't think of any example why this would be super meaningful other than it's just like something fun that you want to do, which is totally worth it. But I don't know, maybe this is what you want to do. Okay, so I'm saying get ACS state, and I could just use Tigris too. I don't know why I did this, but I'm grabbing educational attainment for the entire state, or for all states rather, and grabbing geometry equals true, and then I'm getting Oregon, where I'm saying filter all of the states where the name is equal to Oregon. So this is actually going to be just a one row data frame, but it's going to have a list column for the geometry of Oregon. Okay. Then I have to actually convert this to an SP object because of what I'm going to do next, which is get the elevation data. Okay. So as, and then I give the object spatial. Okay, that makes it as an SP object. Then there's this library called elevator. Okay, and it's meant specifically to get elevation data for you on a spatial polygons data set or a spatial data set generally. Okay, so I say get elev raster, the SP, and then Z is like basically the definition, like how much definition do you want in this raster. So the higher the number you put there, the more time this will take to go and download the data, but also the more precise your, like the smaller the pixels will be in the raster. Okay, so I'm getting Oregon elevation. I'm getting lane 2, but I don't think I actually use that. I don't know why that's there, but I'm getting all of Oregon elevation data. Okay, now with TMAP, I can actually use that elevation data straight away. And what's nice here too is notice I'm also actually mixing SF data with SP data, and TMAP has no problem with it, right? It can take different things on different layers. So I have TM shape, Oregon elevation, then TM raster. And then I just say there is no midpoint. That'll assume 0 is the midpoint. And then style continuous for a continuous scale. And then plus TM shape county. So here's my vector data, right? Which is also SF data. TM borders color is equal to gray 60. So now, you know, there's a map of the elevation of Oregon. It's not great though. And part of how we can fix this or make it better is just to change the color scale. I wanted to, like, there's really good color scales that are out there that you could just use, but just for fun, I wanted to try to create my own color scale. So I did. This is how I did it, right? Style continuous. And then I fed it a palette that has basically a low value, a little bit higher, a little bit higher, a little bit higher, all the way up to white, which is the highest value. Okay. Legend outside true. All the rest of this is the same. So basically, I'm manually feeding it. It's a palette right here, and then I get something that looks like this. The gray for the lines is probably not great there anymore, but I'm trying to basically emphasize the elevation, right? So the wider is higher, and then you get this blue out here too, which is like the ocean. So that's kind of neat, I thought. With TMAP, you can also do totally crazy, amazing things. This looks like something that would be on the wall of an elementary school, right? And that is TMAP code to create that, which I think is pretty darn cool. And that uses raster data and etc. There's an article about TMAP in I can't remember the journal right now for some reason. But anyway, I can get that to you if you want. It has a whole bunch of different maps like this. And if you go to, let's just do it real quick. TMAP, if you go to the TMAP website, let's see, then he has, so here's a bunch of different stuff, right? So these are like a lot of the things that are in the article as well. And if you click here, he has article reproduction code. So here's all of the code to produce all of the figures that are in the manuscript, which is also super nice, I think. Okay, so I just grabbed the code from there to produce this here in the slides. If you want to create interactive maps, it's super easy. All you do is say TMAP mode is view. That's it. And then you create the code, run the code, and now all of a sudden I have an interactive map. And look, my actual county names are there now. So there you go. For some reason they don't work on the other one, but they did on this one. And this also has some nice things too, like it has this hover effect that gives you just the county ID, but you can click on it too and it'll give you the estimate and things like that too. And that's all just by saying mode is equal to view. You can also switch things like the street map view or the topographical view. You can take off the centroids, take off the county, whatever. Okay. Pretty darn nice, I think. Map view is an alternative that is also super quick and easy for interactive maps. I have that county data set, right? And all I do is say map view on county, and this is what I get, which is pretty crazy, I think. And it has a lot of these same things. You can, you know, go to a dark theme or OpenStreetMap, right? And again, you can click and you get all this stuff on the data set. You can also just say zcol, z, right? Color is estimate, and then you get something that looks like this. And again, you can click to get a table of all of the stuff. If you want to make that table a little bit more customized, you can just use from this leaf pop-up table county and say, I want just the name and the estimate. And now we have that, right? The name and the estimate. Okay. This is, to me anyway, sort of astounding. Like that this much code creates a map like this that is pretty interactive and pretty nice, right? Okay, we have like 4 more minutes. The rest of these things are totally not super important, but again, just sort of awareness things. I've mentioned before that the actual geographic size of things can skew your perception of like how much there is. So there's this package called state bins that's sort of a nice alternative when that ends up being problematic, where you can basically just force each state to be a square, and then you just put the states in roughly their location in the United States, and you end up with something that looks like this. And so then perceptually, it's a lot more uniform. And if you're really trying to communicate the value of a variable across the United States, this might be a good alternative. There's also these things called cartograms. I'm not really going to go through the code, but I'll show you an example of what it is. So here's all the counties in Oregon, right? And I'm filling by the population, or no, rather, I'm not filling by anything. But this is, you know, if we were just to look at a map of the counties that looks like that. What we're doing here is we're sort of manually obscuring those polygons based on the population of the county, okay? And so if there's more people, that polygon grows, and if there's less, it shrinks. And so we get something that looks really funky like this, but what you end up with is, you know, a map sort of thing that shows that most of the population is focused on the West in Oregon, in the West, right? You can do the same thing for all the states in the country, and you end up with something that looks like this, right? So you can see California's all bulged out, Oregon got shrunk down, New York's bigger, etc. Okay. So last final note of all of this geography stuff, you may or may not like cartograms. They're kind of like weird, and they are a little bit controversial. But the important thing is make sure that you're not lying with maps, because it's very easy to do that, right? And so this is an example from the 2016 election where if you just fill in every county by whether that county voted for Trump or Hillary, then the whole country looks red. But if you actually break it apart and make a circle based on the number of people that are in that county, then you get a much different picture, right? So this is an example where you can lie with maps, sometimes not on purpose, and sometimes on purpose, right? And so be careful not to lie with your maps. Okay?